Welcome everybody to what I think is our first local group meeting since the start of lockdown. So we're delighted to have Chris Jewell speaking today. I've got a short intro, and I don't know if Chris wants to set up his slides while I go through this. So Chris trained as a veterinary surgeon and then did a PhD in MCMC for infectious disease models, which, if I remember right, was focused on foot and mouth data. Chris also has interest in computational statistics and high-performance computing, and is currently senior lecturer at Lancaster's Centre for Health Informatics, which maybe it says this on this slide actually, which is part of the medical school. And Chris has been involved in the COVID response, I think as part of the government's infectious disease modelling group SPI-M, and also in the Juniper Consortium, which is on the slides. Joint Universities Pandemic and Epidemiological Research. And as well as all this, when Chris was a PhD student, he helped teach me R as part of my master's degree in 2006. So very useful lecture on R, and also some confusing stuff on using R within Emacs, which it took me another couple of years to fully master, but sort of put me in the right direction for using R at the time. Okay, and this is Chris's title, so I'll hand over to Chris at this point. Thank you very much for speaking to us today.
Lovely, thanks very much, Dennis. So yeah, I didn't really realise that I'd be giving this talk on the anniversary of the beginning of the first lockdown. But COVID has kind of become my life since this time last year, and in particular, trying to port some of the methods that I'd previously developed both at Lancaster in the olden days, but also at Warwick University for looking at livestock diseases. And as Dennis says, I come from a very veterinary background, but I think really I'm a frustrated software engineer. So these days I spend most of my time thinking about computationally intensive Bayesian algorithms for various infectious disease applications. And really, when we approached the SARS-CoV-2, as we now call it, epidemic just over a year ago, we very quickly realized that there was a bit of a hole in the statistical toolbox for working with pandemics on the scale of kind of national human populations. So I'll outline some of the things that we've done to try and fill this hole. It's by no means perfect work. And right at the end, if there's enough time, I'll talk a little bit about the challenges that we've faced in terms of trying to develop some new statistical tools at the same time as providing some fairly operational forecast predictions, call them what you like, for the scientific pandemic influenza group modeling, SPI-M, of which I'm currently a member for my sins. So this is the COVID-19 situation as of yesterday. And in contrast with what this would have looked like a year ago, I'm happy to say that cases are very well and truly on the downward trend. So I've plotted the time series of positive tests per day, all the way from Christmas Day right up to the present, and you can clearly see the January peak of cases. And we peaked at about 80,000 cases per day in the entirety of the UK, and now we're down to around about 8,000 cases per day, which is still non-trivial. And there are things to note about this data set, not least the marked kind of weekend effect that we see, these weekend troughs. Turns out that people don't really go and get tested at the weekend as much as they do in the week. So that was a feature that kind of emerged in the middle of last year as the testing program really got underway. We weren't really able to see this weekend effect prior to then. And the other thing that characterizes the outbreak is marked spatial foci of infection. So what I've done in the map on the right-hand side is just plot the absolute number of cases that we saw as of Monday. And you can see that there's a spatial cluster right in Glasgow in Scotland. It's not matched by Edinburgh on the other end of the central belt. And this really stubborn area in West Yorkshire, particularly Leeds and Bradford, are still very high incidence regions. And Birmingham always sticks out, and Birmingham sticks out because it's just got an awful lot of people in it. It's our largest local authority in the country. So in some of the maps I'll show, Birmingham will stick out like a sore thumb, but just be mindful of the fact that there's a denominator issue in Birmingham. So the point of this slide really was to emphasize the dynamic nature of the outbreak. So cases look as though they're decreasing according to some kind of exponential decay law, which is kind of consistent with epidemic theory at the moment. But there are wrinkles in the time series. And there are also these very marked spatial clusters of cases that occur in the country. So what are the kind of questions we're asked? Well, no secret really, these questions have been around in the media for 12 months now. But essentially we observe through case testing, we observe case incidents, the number of new cases of disease per day. And we need some way of trying to turn that incidence metric into a prevalence, so a proportion of people who are infected at any particular time. The reproduction number is of interest, and I don't think this has really been explained well, but reproduction number is, certainly from a statistical viewpoint, an expectation over the number of further people you're going to infect on average if you were to get infected during the epidemic. So it's a measure of where the disease is most likely to take off if it gets infected. And that's rather different from prevalence, because it's perfectly possible to have an area which has a high reproduction number but a zero prevalence. It just means that the disease hasn't got there yet. But if it does get there, it's going to be a problem. And then beyond those two metrics, then there's, of course, a lot of interest in the future trajectory of the epidemic. And that's important not only from a national point of view, thinking about lockdown measures and that kind of thing, but it's also really important locally for local NHS trusts to be able to order in the PPE kits, the testing kits that they need in order to manage the epidemic in their area. So there's a cross-scale element to this as well. So given that that sort of dynamic nature of the epidemic, stochasticity in the numbers of cases that we see from one day to the next, and also this spatial clustering, we set ourselves the challenge of trying to use some of the ideas from livestock epidemics we'd worked on previously and trying to apply them to the UK level. And here we were really thinking about our 380 local authority districts. Why that level? Well, it's just about a tractable number of spatial units in the method I'll outline. But it also maps very naturally onto the sort of the most granular unit of spatial tier lockdown allocations, if you like. So it seemed a sensible level at which to model. There are lots of sources of data, and we wanted to fold those in. So you can think of case testing data, so the occurrence of new cases as being some kind of outcome variable. This is the number of new positive tests per local authority per day. And then we've got some covariate data, which kind of varies depending on what the government are doing with their lockdown measures from week to week. But the most important ones are population size in each local authority, and also measures of human mobility. So how do people move around the country and carry infection with them. Turns out that a Bayesian paradigm is firstly very natural to think about if you happen to come from a very applied background, but it also provides us with a toolkit to fit these models in the presence of censored data, and to do so, of course, with full uncertainty quantification. And if we can do that, then of course we can follow through with that uncertainty and into our reproduction number case exceedance metrics, which I'll show you at the end, and measures of incidence and prevalence that we need for control planning and choosing some kind of optimal or near optimal control strategy. So this is how I tend to think about the case data, and I thought I'd put this slide up just to kind of get straight in everybody's mind before we dig into the model, kind of what these data look like. So on the left is the case time series. I've just plotted that again. That's just aggregate for the whole UK. But if we break it down by local authority, so in the matrix plot on the right, I've got local authorities enumerated top to bottom, and then I've got a time scale in days along the horizontal axis. And the things of note are that we've got these kind of clusters in yellow. So that the yellow elements of this matrix are log base 10 of the numbers of cases observed that day. We've got 22nd of March on the right hand side of this matrix, and we've got Christmas Day on the left hand side, just to give you a timescale. And you can see that in some local authorities, so the ones towards the bottom are around in the northwest, ones right at the top are kind of over towards East Yorkshire, and the ones in the middle include some of the London local authorities. And what we're seeing is that in other local authorities where we've got a white element, we've actually got no cases at the moment. So there's quite a lot of heterogeneity in terms of case incidence. So I think everybody's an expert in SEIR models these days, so I probably don't need to spend too long talking about this, but we sort of think about a disease progression model at an individual level. So we think about an individual such as myself being currently immuno-naive, susceptible to the disease, and I will have exerted on me some sort of hazard rate, a hazard of getting infected or a hazard of getting exposed to the SARS-CoV-2 virus. And if I'm exposed, I consider myself as infected, but not yet infectious to other people. In other words, I'm going to undergo some kind of latent period of virus multiplication within me. And then at some point, I'm going to transition into this infectious class, the I class, and then having got infected, hopefully I'm going to get better and I'm going to recover from the disease with solid immunity. Or if I don't, and I don't make it, then either way, I sort of play no further part in the epidemic. So I'm, in some sense, removed from the population. And so the parameters of interest here are really this infection hazard rate. And we tend to break down the infection hazard rate as a function of some kind of time varying baseline hazard. And then think about the number of individuals within my own local authority who are currently infected and might be pushing on me with kind of infectious pressure or infectious hazard. And then we add on to that infectious pressure that might come from commuters coming into my local authority from all other local authorities in the country. And this matrix C is just a measure of human mobility. Here, the results I'm going to show you, we're actually using census 2011 mobility data. We've, of course, put in a call to the ONS to expedite measures of mobility from the census on Sunday to try and get an idea of how people's movement patterns have changed, particularly in recent times. And then beta 1 then is our kind of relative hazard rate from somebody who is commuting into our own local authority versus somebody who's already in our local authority. These are commonly known as meta-population models in the epidemic literature. The other thing we do is we divide through by the number of individuals in each local authority. And the reason why we do that is because if you think of yourself as an infected person, you're trying to infect others in your local authority. And if you live in quite a dense local authority, well, you probably still have sort of 15 friends that you see per day. If you live in a much less dense local authority, then you probably still have 15 friends, but you just get in the car to go and see them. And so this kind of sort of density independence property of disease transmission is something that we observe commonly in epidemic situations. So how do we let our baseline force of infection change? Well, this is a fairly crude model. So what we're allowing at the moment is for our baseline transmission rate to change every 2 weeks. And we've actually put a Gaussian process on those kind of 2-week varying baseline hazard rates. It's a little bit of an odd construction because it's not strictly continuous everywhere because of these step changes. But nonetheless, we kind of use the Gaussian process as a useful tool to kind of create some notion of dependence between our 2-week intervals. And then, of course, we have a weekend effect as well. And the bit that I skipped over in the previous slide was we have this removal rate, gamma. And if we assume that actually a positive test is a proxy for observing somebody moving from the I class into the R class, hopefully you go home and self-isolate if you're positive, then we can think about our sort of detection rate, gamma, as being a function of time, so gamma t. And then if we're in a weekday, we can say that gamma t is gamma naught times gamma 1. Gamma 1 is kind of like a comparison between being detected on a weekday and being detected at the weekend. So how do we actually set up the kind of time series aspect of this SEIR model? Well, we think about a Markov transition rate matrix, essentially. So our Q matrix, Q sub M, thinking about a single meta population. So this is thinking about how we get from our configuration of SE INR, so the number of individuals in SE INR today, to think about how we propagate that state to SE INR tomorrow. So the usual theory, we put in our transition rates. So we've got lambda t sub m for the infection hazard rate within metapopulation M. We have nu, which is our rate of transition from E to I, and gamma, which is the transition rate from I to R. And then we arrange this so that the diagonals are essentially the sum of the non-diagonal row elements. So each row now sums to 0. And then we can turn this into a Markov transition probability matrix just by taking an exponential, a matrix exponential, or approximation thereof. And then the way we propagate our state is then to take a multinomial draw along each row of the transition matrix to decide who stays put in their own epidemiological class and who moves to each successive class. And that might seem like a complicated way of implementing what is just a linear discrete time state transition model, but it allows us to be quite flexible and embellish our SEIR model, put branches into it, put coalescences into that state transition model. Now, so the issue with our epidemic process is that we have three state transitions. We have S to E, E to I, and I to R. And we're assuming that the only state transition we observe is I to R. Okay, so we have this green and yellow event matrix only for the I to R transition. And we regard then the actual infection event, so the S to E transition, as being censored, and as well as the E to I, so the onset of infectiousness, being censored. And that kind of makes sense for an infectious disease because, you know, for a common cold, you might meet somebody who infects you with a cold, but you're not going to know that you've been infected until sort of 3 days later when you start coughing. And for COVID, that actually might be anywhere between about 4 days and 8 days later. So somehow we're going to have to deal with these censored observations. And there are actually two types of censored data in this model. There's what we call partially censored event times. So these are S to E and E to I events for individuals who you've already observed an I to R event. So the thing is, you know, for these individuals, you know the number of SE and EI events in this matrix. You don't know, but you just don't know quite when they happened. The other type of censored event time is for individuals whom they have undergone an S to E event, and they may or may not have undergone an E to I event, but they're yet to be detected. We're yet to observe their I to R event. So these are what we call occult infections, or kind of like fully censored infections. So this is just to make the point that for this kind of multinomial or chain multinomial model, Markov discrete time Markov transition model, the likelihood is kind of beguilingly simple, really. It's just a product over log transition probabilities and log numbers of events that happen per day. But the fact that we've got these censored event times, these two matrices of censored events, makes actually inference on these models, unbiased inference, rather more complicated. So how are we actually going to fit this model? Well, epidemic models have been used as motivating examples over the last kind of 10 years, very much in kind of likelihood-free methodology literature. So ABC algorithms through into pseudo-marginal algorithms, into particle MCMC algorithms. And those algorithms can be highly effective, and they're simple to implement. And if you've already got a disease simulator, as many epidemiologists do, then it's kind of easy to embed that simulator within the fitting methodology. But they tend to start to lose efficiency when the dimensionality of your kind of particle update is high. And in this case, we've got these kind of 380 coupled time series of epidemic processes in each local authority, coupled by our mobility matrix. And we did some sort of early experimentation a little under a year ago, just with some simple filtering methods. And we actually concluded that without a lot of noise, without a lot of work, the process noise, so the case observation noise, was so high at that point that actually it was unlikely that we would get these methods to work effectively. So that left us to fall back on data augmentation MCMC, so a direct data augmentation of the censored events, treating them as parameters within our Bayesian models. And we've used these algorithms previously, but we've used them in models where you consider each individual in the population, in some sense, as its own metapopulation. And we know that these algorithms, they work quite well for individual level models. For example, for populations up to about 200,000, so the foot and mouth susceptible farm population in 2001 in the UK, it works quite well for. It works quite well for populations of chicken farms for high-path avian influenza, and it also seems to work quite well for small village populations for diseases such as visceral leishmaniasis, one of the neglected tropical diseases. But actually, it turns out that they haven't been used. These kind of data augmentation methods haven't been very well studied in these kind of discrete time models, much more studied in continuous time models. But they do have this rather nice property that you condition directly on the data that you've observed. So unlike a filtering method where you have to sort of predict your observed data and then choose predictions which are more consistent with the data than others, here you just condition directly on the data. So, so how does this work? Well, what we're going to do is construct a Gibbs sampler, essentially, that first of all samples, perhaps jointly, over the transition rate parameters in the model, and then we're going to draw from the conditional posteriors of each of our matrices of missing data. So I've denoted our S2E matrix and our E2I matrix as Z here. And there are two types of moves that you can do within this missing data. And as I said earlier, we have this concept of partially censored data. These are event times that you know exist, you just don't know quite when they happened. And also these occult or completely censored events, events which might have happened, but because we haven't observed the eye to eye yet, we don't kind of know how many of those events exist, let alone when they happened. So it's quite a high dimensional problem, and certainly with these event matrices, we've got two event matrices, and each of them is a number of time points. In this case, it's 12 weeks, so 84 days, times our 380 metapopulations. So the task is then to design some sort of Metropolis Hastings sampler to get around all this, this missing data. Okay, so that's just a summary of the MCMC. So how might we go about updating, well, first of all, partially observed event times? Well, what we could do is we could propose to visit a metapopulation, and we have to visit a metapopulation conditional on the fact that it has events to move. Certainly in low incidence settings, if we go to a metapopulation that doesn't have any events to move, it's kind of a wasted move. So we condition on there being events to move, and then within that metapopulation, we propose a time point, again, conditional on that time point having available events to move. And then we propose to move a subset of those events, x star, a distance delta, either forwards or backwards in time, recompute the likelihood, and work out the accept-reject rate for the Metropolis step in the normal way. But it actually turns out that if you do that naively, you get a really bad algorithm. And I'm going to skip the maths and go onto the picture. But this is the reason why. So in the epidemic model, each of our compartments, S, E, I, and R, at any particular time and in any particular metapopulation, has to be at least 0. You can't have a negative number of people in a compartment. And so the way to think about this is that we've got 3 counting processes going on. So if I denote NSE T the number of SE events that have occurred up to and including time t in a particular metapopulation. Likewise for the EI event and the IR event. Then there's a natural ordering of these counting processes, which is easily seen by just plotting them. So what we're saying here is that if the blue curve is just the counting process for the S2E events, then we're saying that the orange curve, which is the counting process for the E and I, has to be at most equal to the blue curve. And similarly, the green curve, counting process for I to R, has to be at most equal to the orange curve. And if these curves switch order, switch rank, then we invalidate our epidemic, and one or more of our S, E, I, and R compartments at any particular time point is likely to go negative. So we have to respect these constraints when we're deciding to move infection times around the geometry of our epidemic space. So that's moving partially observed events, and we can do a similar move for our occult events. So again, we choose a metapopulation and time combination. We choose at random a number of events to add to that particular cell of the matrix, and then we calculate the likelihood in the normal way. And again, we have to choose our X star number of events carefully so that they respect the counting process constraints. And the reverse move then is to delete these occult events that we've already added. Okay, so having decided how we're going to update our missing data, then we can just run our Gibbs sampler, and typically we'll run this for around 200,000 iterations. We'll take a good wodge of burn-in and thin by every 20 iterations or more. And in the MCMC scheme, what we typically do is 35 updates of randomly selected cells in our Z matrices per update of transition parameters. And that seems to be reasonably optimal to allow everything to burn in a reasonable time. There are 2 or 3 other choices that we've made. So first of all, we don't add occult infection times for the whole of the time window that we're analyzing in the model. We actually only do it for the last 3 weeks. And the rationale behind that is if you've got occults that have occurred sort of more than 3 weeks ago, then actually it's overwhelmingly likely that you will have detected that infection by now. So there's no point in training the occult sampler in on that kind of bit of the time series. It's just going to reject moves for the vast majority of the time. So it's a small approximation that we've made. And then there are choices or MCMC optimization choices really of the sort of maximum number of events that you choose to either add or move per updated Z. And that, essentially those are tuning parameters that we've chosen by looking at maximizing the mean squared jumping distance of our event time moves. But this is still computationally intense and potentially takes a very long time. And so we've actually implemented this using Google's TensorFlow and TensorFlow probability, and all credit goes to the team in New York that have been really helpful to us, advising us on how best to use their software to get this to run quickly. So we've got it down to about 4 hours, 20 minutes, which runs fine in an overnight time frame. So this is just saying what I've just said, really. The TensorFlow probability library offered us GPU compute for very little development time comparatively. I've written CUDA kernels in the past to implement MCMCs, and it's not something I wanted to do in the hurly-burly of actually trying to provide operational results for COVID at the same time as trying to drive the statistics forward. And of course, it wasn't quite a silver bullet, so there are lots of things missing in TensorFlow probability. It's still under very active development. It's still a very, very early project. So we've actually worked with the guys in Google to come up with a load of extension modules, which you can find if you go to our GitHub repository. The link's at the bottom there. But extensions such as a few implementations of some missing random variables, uniform integer random variables, our bespoke event time and occult update metropolis steps. And the big feature that was missing from TensorFlow probability, and to some extent still is an ability to construct a metropolis within Gibbs sampler. TFP has taken a very kind of Stan-like view of the world where everything can be done with Hamiltonian Monte Carlo, except the problem that I got here, of course. So we've had to build a module that allows us to do Gibbs sampling. So, as I say, this is not a perfect solution. It's a solution that we've developed rapidly over the last 12 months, whilst spending a lot of time doing some fairly operational work. So you can see that the MCMC traces on the left, even though they're heavily thinned, they do appear to be at least stationary, but we could do a lot more to increase our effective sample size across the trace. Interestingly enough, one parameter I did put up here is beta 1. So this is the top row of plots, and beta 1 is the relative infectiousness of a commuter versus somebody in your own local authority. And currently, this is right down at about 0.2%. And why is that interesting? Well, back last summer when we first brought this model online, we were looking at values of about 0.6 for this parameter. So that was saying that, you know, a commuter or the amount of infection that you were getting into your own local authority was about 60%. So you were about 60% as likely to get infected by somebody else from outside your local authority as you were somebody inside. And that's dropped now to 0.2. So it looks like lockdown really works, stops people moving down the country. Given that cases are going down, it's probably true. This plot highlights two things. Well, first of all, the black line is just the data. So these are the total number of events per day that we've observed over the last 3 weeks, I think. And in the pink and the blue lines, we've got the estimated number of S to E and E to I events per day. And you can see that there's some uncertainty there, which is the sampler exploring the various combinations of SE and EI events that are consistent with the model. And one of the artifacts in this is this big jump in SE events that occurs about 2 weeks ago. And that really is our 2-weekly time varying infection rate kicking in. That's a boundary between these discrete time epochs. And what it's basically saying is actually cases have leveled off in the last 2 weeks, and we've got a higher baseline hazard rate as a result than we did previously when cases were falling. But because of that discontinuity, we get this jump in our parameter space in the number of S3 events, which is not quite sort of biologically satisfying. So one of the directions of travel for this is to actually get rid of that 2-week interval and actually look towards a non-stationary autoregressive kind of Brownian motion for our baseline hazard rate. So then some results. So I thought everybody might be interested to see the Nowcast that we did as of yesterday. So these results will go forward to the SPI-M meeting tomorrow morning. And what we're seeing in comparison to the previous week is that, so last week, all our reproduction numbers were well below 1. We were happy. This week, and this is a posterior mean, our RT values have jumped up and they're just beginning to touch 1. And the conjecture is that actually this is in response to, unfortunately, the kids going back to school. And we know that it happened a little bit earlier in Scotland than it did in England, again, consistent with the fact that the kids went back a bit earlier in Scotland. And on the right, you can see our 2 weekly time varying RT measure, and you can see how it's jumped up. So I expect we'll be monitoring that extremely closely in the coming weeks, as and particularly on into next week when the next derogation of the lockdown laws happens. This is just a slide of the Nowcast for our absolute case incidence, model smooth case incidence, and also the prevalence of disease around the country per 10,000 individuals. And there's a certain amount of shift going on because, again, a couple of weeks ago, we saw a hotspot in our usual suspect areas, Leeds and Bradford and kind of West Yorkshire, but it's actually pushed eastwards into North Lincolnshire now. So this is kind of a new phenomenon and is perhaps a new spatial wave of disease going across the country. So just to finish off then, a few comments around sort of personal experiences through this. So it turns out that real-time epidemic modeling is actually hard when you're also trying to develop new statistical techniques to block up holes in the analytic toolkit. And so there's always this tension between spending time doing research and development and spending time writing weekly reports and pulling together data into various GIS frameworks. TensorFlow has helped us, and the GEM project, which is Wellcome funded, which is an attempt by us to develop a probabilistic programming language for epidemics, has certainly made that process quicker than it would have been perhaps 5 or 10 years ago. And GPU acceleration available through TensorFlow and TensorFlow's sort of tensor abstraction features has really helped. And the other thing that's helped is pipelining and automation of our analysis. And this was really facilitated by the government pulling online the coronavirus.data.gov.uk website, which all of a sudden gave us an easy, automatable way of sucking in our required positive test data. So we now have a regular job that's scheduled that goes off at 9:30 every night. It automatically pulls in the latest data, latest case data from the government website. The GPU-enabled algorithm kicks off on our high-performance computer at Lancaster, and then right on the end of that analysis, which goes through inference and prediction steps, it puts all the results into a research storage archive that we have running in our VM pool. And then in the morning, so tomorrow morning, what I'll do is access summary of the latest results down onto my laptop, put the PDF reports together, and they'll go off to SPI-M. But because we're doing this every day, and I don't want to be doing that every morning, there is also an automatic web visualization, the link for which is up at the top. So, oops, there we go. So this is the website by which we can visualize various metrics like our daily absolute case incidence, albeit on a slightly different color scale, our prevalence, if that'll update in a minute. It's the trouble with doing live web things. And the other thing that we look at is in-sample prediction over the last week and over the last 2 weeks to actually point out any areas that are behaving atypically compared to what our in-sample time series prediction might be. So we're currently slightly worried about so somehow we're slightly worried about North Lincolnshire, for example. We're just seeing the cases rise a little bit above what we're predicting from the model currently. And we can do this for various other areas around the country, of course. And this has really helped us, particularly with local health authorities, because they can just come to the website if they want to know what the daily case incidence is. For example, in Lancaster, then you can get a time series prediction, which you can step through graphically, and see how it changes over the next few weeks. And if you want to, then you can download the raw data. And we know that, for example, Lancashire Health Authority do this to help with their planning. There have been some challenges in doing this, and actually I think that academic institutions are not set up particularly well for constructing these kind of analytic pipelines. They're set up for the R&D bit, but not for the kind of online day-to-day operationalization of these models. And particular challenges we've faced are challenges around getting the various links in this pipeline to talk to each other through authentication and authorization protocols. And there's also a certain amount of sort of fundamental interoperability issues between the various different bits. So for example, our high performance computer at Lancaster is really quite isolated from the archive storage. And then the archive storage is isolated from the rest of the world. So it's hard to get collaborators to just kind of tune in and help with unpicking MCMC results and that kind of thing. So again, that's kind of an informatics dimension that we're trying to sort of work on, and particularly use cloud computing techniques to try and resolve. And then further developments on the model. Well, we've got a lot of work to do on this time varying force of infection. This is something that people haven't really done that much to date. If we're going to have a time varying Brownian motion, we will need Hamiltonian, Monte Carlo, and related algorithms almost certainly to work in that kind of dimensionality. And the other thing that we need to do is to work harder and develop our data augmentation methods, particularly expanding our kind of single time point metapopulation moves to try and move more time points or move more metapopulations at once, still respecting the kind of geometry and the interlocking geometry of all the metapopulations. So that's kind of an active field of research for us. And the other bit, I mentioned the GEM project, but we also have, as Dennis mentioned, the Juniper Consortium of 7 universities working on COVID database research. So within that, we've got some projects that are expanding the GEMLib, the TensorFlow probability modules that we've been using to do our analyses. And then finally, I'd just like to thank a couple of colleagues, well, 3 colleagues. So John Reed, who's an epidemiologist in my group, who's been absolutely brilliant for adding a human epidemiology dimension to this model. Barry Rollinson, who some of you will know, who's a geospatial research software engineer, and Claudio Fontera, who has been working on COVID modeling in Africa as part of the Neglected Tropical Diseases Consortium funded by Gates. Department for Health have been absolutely unrelenting in their efforts to package up data, which led to the coronavirus.data website. Also Graham Medley the chair of SPIAM for providing an awful lot of moral support and encouragement to our efforts. And then finally, of course, Office for National Statistics, without which we wouldn't have all our human mobility data, our population data, and now data on things like observed prevalence and seropositivity, which we look forward to using fairly soon. Thanks very much.
Okay, thank you very much, Chris. I'll just pause for virtual applause. You might be able to see in chat or in people's video screens. Are you able to stay around long for questions?
Yeah, sure.
Okay, brilliant. So if anybody would like to ask a question, please raise your hand in the participants list, and I'll ask you to unmute. And I'll keep the recording going during questions as well. Okay, so Sarah Heaps has her hand up.
Hi, Chris. Thank you for a really interesting talk with a slightly pessimistic outlook.
Yeah.
I was just wondering, so with all this fitting going on kind of automatically and overnight, do you check kind of MCMC convergence diagnostics, or is that kind of just assumed to be okay?
Yeah, no, absolutely we do, because the bit that I haven't dwelt too much on is the fragility of this MCMC. So the laptop bit of this chain is an automated report that basically, just gives me the usual trace plots for all the parameters, and then if visually we suspect that something's not too good, we can go in and we can start looking at all the usual kind of convergence diagnostics, also correlations and that kind of thing. So it's kind of a nice way of being able to sort of provide a daily resume of how the algorithm's performing, and allow us to kind of go in and dig a bit deeper if necessary.
But what would you do if you decided that it hadn't converged?
Panic. So it has happened, and there have been reports that we've actually declined to send into SPIAM per week. It doesn't happen often, but it has happened over the last 12 months, and so we just don't. And then we spend a frenetic day kind of trying to work out why the sampler hasn't performed. Maybe the initial burn-in adaptive MCMC has gone wrong in some kind of way, and we try and fix it. So it's a little bit ad hoc, but I guess with an MCMC with some fairly high dimensional and fairly experimental samplers going on, I guess that's kind of what you get at the interface of the R&D and the operation.
Okay, thank you very much.
Okay, Darren has his hand up.
Hi, yeah. So again, thanks. Really interesting talk. I just want to ask you a little bit about TensorFlow, actually. So as you sort of hinted at, it probably wasn't really developed with, well, probably with MCMC in mind at all, in fact, when it was first developed, and certainly not this kind of MCMC algorithm. So do you think that actually it will ultimately represent a good platform for developing these kind of MCMC codes, or do you think there'll always be a bit of an impedance mismatch there with this kind of algorithm in TensorFlow?
I think it will be good, actually. I mean, fundamentally, TensorFlow is really good at doing matrix operations, and for the kind of model that I got here, that's great, because I can operate on those event matrices very, very quickly. And we've certainly found the tensor abstraction to be brilliantly useful for, we've essentially got stacks of those transition matrices over time, over meta populations, and ultimately over MCMC iterations. So that's been extremely useful. I think the TensorFlow probability library, which gives us all the probability distributions and some fairly sort of fledgling MCMC algorithms, it's in massive development at the moment, and the capability of it seems to have doubled in the last 6 months, and there are some enormously keen developers working within Google on it, one of whom is Colin Carroll, who has worked extensively on the PyMC3 project, which is much more mature, albeit underpinned by a now obsolete maths library. So I think it's a case of watch this space. They've gone hook, line, and sinker into the kind of continuous space HMC one transition kernel. So you don't really have a Gibbs metropolis within Gibbs architecture. And I think they're now at the point of sort of working out what to do next. They've certainly crawled over our Gibbs framework and have pointed out all the design flaws in it. So I think maybe in 6 months or a year's time, we might see something that's a bit more capable in MCMC than it currently is.
Yeah, okay, and maybe just a quick follow-up then. In terms of GPU utilization, how are you kind of parallelizing? Is that just over spatial areas, or are you doing other things as well?
So the sort of the major win really is the likelihood computation. There we go. So it's basically just like a quadruple sum over transition matrices in the blue and then metapopulations and time periods. So the GPU is really efficient for that. And where we seem to get the win with TensorFlow is, unlike my sort of previous hand-coded attempts where I was essentially using the GPU as a likelihood processor, which meant that I had to, for each MCMC iteration, I had to fetch back a value of the likelihood to evaluate an accept-reject ratio, and then push back new values of parameters to the GPU. Everything here happens on the GPU. And you've also got the just-in-time compiler XLA, which, as long as you use it correctly, can just be a bit mindful of some of its restrictions around arrays, fixed array sizes, and that kind of thing. It actually appears to be really quick, and my sort of GPU metrics are kind of 98% occupancy throughout the runtime, that kind of thing. So I'm quite positive about it. I wouldn't say that I am getting the efficiency that I would get if I'd have spent the last kind of 12 months writing a hand-tuned CUDA kernel in C++. But I think it's a nice compromise between development time and GPU acceleration, really.
Yeah, cool, thank you.
Okay, so do we have any other questions? Andrew Golightly's got his hand up.
Yeah, hi, Chris. Just wondering if it would really mess up your data augmentation scheme if instead of assuming you observed removals, you assumed that you observed E to I transitions and then stuck an observation model over the top, like binomial or something.
Good question, because that's next week's task. So yeah, so certainly the framework's going to work. Whether the algorithm works well, I don't know yet. So what we're thinking here is, currently we're sort of making the rather swinging assumption that all the positive tests we see are all the positive tests that there ever were, which is of course a huge assumption. So actually what we'd like to do is put some kind of, as you say, observation noise around that, to say that, one day we will observe 80% of the true cases, the next day we might observe 60%, etc. But there's no real reason why within that framework, thinking about it as a hierarchical model, you put an observation on the I to R events, for example, that you couldn't actually employ the same data augmentation technique on the I to R, and then you just use it for all three transitions.
Might make your mixing worse, I guess, since
it almost certainly will, yeah. But how much worse, I don't really have a conjecture for at the moment.
Yeah, thanks.
I mean, the other way to do this, of course, is in the filtering framework, and I think it might be interesting to think about that. So yeah, up for discussion if you fancy it at some point.
Yeah, cool. Cheers.
So, Chris, I wanted to ask, are people, are other groups inspired using kind of quite different models to look at this data? So maybe deterministic models or something?
Yeah, so I'd say that probably the bedrock of the modeling that's going on for COVID is founded on differential equation models. I think we're the only group that contributes to SPI-M, certainly, that is using a spatial model on which we have principled inference procedures. Imperial have their kind of spatial micro simulation, but as far as I know, it's not fitted in a particularly formal way. There are lots of other groups. So I know Matt Keeling at Warwick, for example, implements all his models as ordinary differential equation systems. He puts then an observation process around those. So you think of the ODE as describing the mean of, say, a negative binomial distribution for the number of cases observed at time t. But you know, he's not looking at space. He's looking at a bit of age structuring, but you know, that gives you a dimensionality of about 6 versus 380. So I think we're sort of fairly unique in what we're trying to do, and you know, it's certainly a hard problem. Hence my comment to Sarah that it's not every day that this thing is kind of suitable for producing results. And you know, as yet we don't really understand. You know, it's difficult to sort of predict what sort of features of the data coming in actually upset the algorithm. So it's quite, yeah, it's nascent, shall we say.
Do you notice that you get kind of any qualitatively different results to the other models? I guess there's so many variables in there that you'll...
Surprisingly not, no. I mean, whatever our concerns about the sort of the marginal mixing properties of the chain itself, when you actually compute a predictive distribution, it actually seems to replicate what's going on quite well. One thing that we do sort of differ quite markedly from other groups on is our posterior uncertainty, which is a lot smaller than quite a few of the other groups. And I've not got to the bottom of this yet, but it could be everything from not assuming an observation model on numbers of cases to ABC algorithms that other groups are using that may be rather overestimating posterior variance. And I suspect in some cases that's true, but that is a difference. We do see a difference in posterior variance and therefore predictive variance.
Okay, great, thank you. Does anybody else have any questions? Andy's still got his hand up, but that might be from the previous question.
Sorry, Dennis, that's my incompetence.
Oh, okay.
Well, I normally do.
Okay, so I guess let's wrap it up there. Thank you again, Chris, for a great talk. We can probably stick around if people want to have any informal conversation. I think we've got some of our RSS local group talks planned, but no actual dates yet. Amir, as secretary, might be able to say something about that.
Yeah, we haven't got any firm dates just yet. We're still in the planning process at the minute, but we have got some lined up.
Okay, brilliant. Right. Thank you very much, everybody.